Nicholas Bramhall. Welcome to the Lab4 report of magnetic field of a bar magnet. Let's get into it. So the purpose of this lab is to find out the magnetic dipole moment of the bar magnet, and we did that by measuring the magnetic field at the phone at different distances from the bar magnets. And afterwards, we built a GlowScript computational model to, first of all, visualize the fields and also compare predicted results, the computation results, with the actual measurements. The result is that we found a moment of 6.08 amps times meter squared, and this is consistent with the relationship that the field has an inverse relationship of, has a direct relationship with the 1 over r cubed. And you can see it displayed in the graph later on. Now, the dipole approximation on the 45 degree was a bit off, which most likely stems from how close the bar magnet is to the phone. So, some physics models and principles. On axis is, the general form up here is that, and then it's broken off depending on whether or not you are on axis or perpendicular, which is the magnetic constant times 2 times the magnetic dipole moment over r cubed. And over here, we can see that there is, it's negative here, and that this is doubled. I'm sorry, I don't have to point you on. This is doubled, and this is negative. And that's the big thing that is important here. And then over here, it's a little bit in between due to the fact that when you do the, this is an approximation, and the direct formula has a lot of different components. So the experimental setup and procedure. So the system is the bar magnet, and the surroundings is the Earth. And we measured the x components of the field along the magnet's axis, and then using that, you can see here on the right all of the data that we got. And so taking the average of it all, we got 6.08, 6.09 in that ballpark. The Earth's field is around 18.5 microteslas. So determining the dipole moment, here's the graph I was talking about earlier, in which we plotted the linear of the magnetic field versus the linear of the distance. And here we've got a nice slope of negative 3.65. And the ideal dipole slope is negative 3, so we're a little bit off from ideal, but it's still pretty close. So that's a good sign right there. The computational model right here, this is the main point in which we created the magnetic field. We simply pass in the magnetic moment that we calculated earlier, and we pass in the distance vector depending on where we're calculating the distance from. And then we use the good old formula, and we return that to get the magnitude of it. So moving on, we have here the GlowScript visualization. We can see that it goes from north to, it goes from south to north, and then it wraps around like it should. And then over here, we've got a bit of an off thing. The 45-degree angle is what this magenta one is here. I'm sorry for waving around my mouse so much. That must be distracting. And then on the right, we have the console output. So it all seems to be in order, before we know. Now, the computed magnitude that we got, meanwhile, the actual measured one, is about 3 times off. And the most likely reason is due to how big the magnet is in comparison to where we had it. As you can see here, the magnet length is not much less than. It's in fact sometimes around in that range. And so this can significantly increase the magnitude and can fill off the air. Of course, it also could just be human error in terms of the position of the phone, and it could also be the limiting factor of the magnetic meter in the phone, because it has a smallish, well, it doesn't have a smaller resolution. It has a area that, a range that it can pick up that can throw off the ratio, but that's very small in comparison to what is most likely just the fact that it's too close. So, the what if we had changed the, if we hadn't compensated the magnetic north, how would it have changed? And ultimately, it wouldn't have changed that much as long as we kept it at that same angle. If we kept it at the same angle, then we still would have been fine because the Earth magnetic field would have been consistent and the biomatter would have been the only one that was changing. And now, what if we had two identical magnets? And so, of course, we can't have them repelling each other, so there would most likely be north to south, then north to south, they would be attracted to each other. And when that would happen, the fields would double, minus a little bit of change due to the distance to the phone. Oh, so it would cancel. Thank you very much.